This video on Riemann sums follows from the previous one, which gave the background and the formula for Riemann sums. Now we're going to have a look how it's applied in two examples. Firstly, it's important to know the following series or to be able to recognize them because they're used in Riemann sum calculations. They are, however, provided in your AP information booklet that you get in the exams. I do actually provide another video where I prove the first three of these series or these formulae, leaving the last one for you to try on your own. But let's see here. I'm not going to refer to the proofs in this video, but I'm just going to refer to actually what these summations add up to. So the sum of 1, so it's 1 plus 1 plus 1, n times is n. The sum of I, that's 1 plus 2 plus 3 plus 4 plus 5, adds up to, this is what it looks like. We can then times it out to that. And often we're going to go straight here. The sum of the first few natural numbers squared, that'll be 1 squared plus 2 squared plus 3 squared plus 4 squared, sums up to that, which then we can multiply out our brackets to get that. Then the sum of 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all up to n cubed, we get that, which can simplify to that, and we're often going to go straight there. So you can use these straight out in your Riemann sums. All right, so I'm going to refer to the method while I'm doing an example. Bearing in mind, remember, this is how we determine a Riemann sum, so we're building up to this. Where change in xi, just to remind you, is the width of each rectangle. F of xi is the length, so if we go width times length, we get the area of the rectangle. We add up all those areas, and then we let the number of rectangles tend towards infinity. So we're going to break this up into steps. Firstly, we find change in xi, we find out what xi is, we find f of xi, we times them, then we add them, then we introduce the limits. Now you can do it all in one go. I just find it easier to break it up into different steps so as not to make any mistakes and to know what I'm trying to find along the way. So let's start with this example, and we're going to draw it just to visualize. Determine the area under f of x equals 8x minus 3. So it's the area under a straight line from x is equal to 2 to x is equal to 6 by means of Riemann sums. All right, so let's just have a look. If we're breaking this up, let's generalize it a little bit. We've got our starting and our ending points, which we said were 2 and 6. Okay, so we've got 2 as our starting, 6 as our ending. Okay, so that's our A and our B. Then this becomes x0. That will be x1, x2, etc. till we get to xi all the way up to xn with our graph f. Right, let's just look at this middle block, remembering that that height would be f of xi, and that each block is a change, it's our width, it's change in xi, each block here. Change in xi. And we'll find out what that actually is now. So we're going to go step by step, and I'm really going to refer to those steps. So, first, step 1. Let's look back at our steps. Determine change in xi. So that's my ending minus my beginning over n. Okay, so my step 1 is change in xi, which is my end minus my beginning over n. And let's look at it in the context of this exact one, this exact example, that change in xi will be equal to 6 minus 2 over n, because remember we're going to let our n tend towards infinity, which is 4 over n. So that's my width of each rectangle. Very important to remember. Actually, let's do it in purple because I did it in purple above. That's my width of each rectangle. So here, this change in xi is actually 4 over n. They all have a width of 4 over n, 4 over n, 4 over n, 4 over n, etc. Step 2. Determine xi. Now that's my beginning plus however many, so it's a plus I times change in xi. Okay, so that's my step 2. Step 2 is to find xi, which is equal to a plus I times change in xi. It's however many widths we need. So let's do that. Xi is equal to a, which is 2, plus I multiplied by change in xi, which we found to be 4 over n from the previous step. I can then simplify to 2 plus 4i over n. Cool. So we've now completed step 1, we've completed step 2, so we've got our change in xi, which is 4 over n. We've got our xi, which is 2 plus 4i over n. Step 3 says determine f of xi. So let's do that here. Step 3. I want f of xi, which depends on the formula. So in this particular one, it's 8 times xi minus 3, because we were given the formula of the straight line as 8x minus 3. So let's do that. F of xi, we know that xi is, in fact, we found it in the previous one, 2 plus 4i over n. So have a look back here. Xi is 2 plus 4i over n. So wherever I see that xi, I'm actually going to put 2 plus 4i over n minus 3. Let's simplify that. I've got 16 plus 8 times 4 is 32. So I've got 32i over n minus 3, which gives me 13 plus 32i over n. Cool. So now I found f of xi. Remember that that is, let's look back again, that is the length or the height. Okay, so that is my height. And it varies depending on which rectangle we're working with. So let's look back now at step 4. I now need to multiply my height or my length times by my width. Multiply them together. So that's my step 4. So step 4 is I multiply f of xi multiplied by change in xi. Right, so let's do that. F of xi, we've got 13 plus 32i over n. And we multiply by change in xi, which we got to be 4 over n. So we multiply them together. We distribute, so we're going to get 13 times 4 over n, which is 52 over n, plus 32i over n times by 4 over n, which is 128i over n squared. So we've multiplied. Let's look at our step 5. Now we've got to determine the sum of that product from I is equal to 1 up until n. So that's my step 5. Step 5. We want the sum from I is equal to 1 up until n of f of xi multiplied by change in xi. Okay, so let's do that. That will be the sum from I is equal to 1 up until n of that, because that is my product in simplified form. So it's going to be 52 over n plus 128i over n squared. Now we're allowed to split summation over a plus sign, so that's what we're going to do. We split it. So it becomes the sum from I is equal to 1 up until n of 52 over n plus the sum of I is equal to 1 up until n of 128i over n squared. Right, now another rule of summations is that anything that doesn't have to do with this variable, with the variable I, can come out. So do you see, I don't even have the variable I. So this all comes out to the front. That's 52 over n. Summation I is equal to 1. We can't leave nothing there, so it's 52 over n times 1, so it's 1. Plus, same thing here, anything that doesn't have to do with the variable I can come out. It's basically like taking out a common factor. So 128 over n squared comes out. 128 over n squared, and we sum, and we're left with an I, and that's from I equals 1 up until n. This is when we go back and look at those series, or those formulae that are given in the formula sheet. So let's actually go back here. There we go. The sum of 1 is n, and the sum of I is n squared over 2 plus n over 2. So we can go straight there. Okay, we can go straight there. So let's go back here. Right, so I've got 52 over n, and the sum of 1 from I is equal to 1 up until n is just n, so I times it by n, plus 128 over n squared, and the sum of I from I is equal to 1 up until n, remember what we got? We got n squared, let's go back here quickly, n squared over 2 plus n over 2. So we're going to go back there, n squared over 2 plus n over 2. N squared over 2 plus n over 2. You can also use it in the other form before you've times out the brackets. Okay. 52 over n times n is just 52 plus, now we've got to times n, 128 over n squared times n squared over 2 gives us 64 plus 128 over n squared plus n over 2 gives us 64 over n. Simplify that a bit further, we get 116 plus 64 over n. So that's usually the most time-consuming step. We then go to our last step. Step 6 is when we introduce our limit. So at this point, we introduce our limit. So let's do step 6. Send our page a little bit. Step 6. Is now when we want the whole thing. So we want the limit as n tends towards infinity of our whole sum of all those rectangles. So we got f of xi multiplied by change in xi. Okay, so we're going to have the limit as n tends towards infinity. Now we've already worked out what that whole sum is. It's that formula there. It's 116 plus 64 over n. Now remember how limits work. If I let n get bigger and bigger and bigger and bigger, then 64 divided by a really huge number gets really close to 0. So that will tend to 0. Tend to 0. Which makes my limit 116. So have I answered my question? Go back. The area by means of Riemann sums. I found my area to be 116 units squared according to Riemann sums. So remember that's just an approx. That's how we get our actual area, 116 units squared. Right, so that was nice and straightforward with a straight line. Let's try one more example, going through all our steps. Right, so let's have a look at this example. You'll often get asked to evaluate an integral. So lower bound is 1, upper bound is 3. This function by means of a Riemann sum, which means you can't use your rules of integration. You've got to use your Riemann sum. And you might find that you can shorten it. I like to go step by step because usually just you can get asked a maximum of one of these in an exam. You don't want to make any mistakes, but if you can shorten it, by all means, please do. So let's go through this example. Starting with our first step, step 1. Our first step is we want to find change in xi. Change in xi. Remember that that is b minus a over n. So our change in xi will be our upper bound, which in this case is 3, minus our lower bound divided by n. So that's 2 over n. Step 2. We want to find out what our formula for xi is. So xi is equal to a plus I times change in xi. So in this case, xi will be equal to my a is 1 plus I times by 2 over n, sorry, because in step 1 we got our change in xi to be 2 over n. So we know that it's equal to 1 plus 2i over n. Okay, then step 3. Step 3, we want to find our height of our rectangles, which is our f of xi. That is dependent on our formula that we were given, our function. In this case, our function is 2x plus x squared, so it's 2xi plus xi squared. So let's do that. We know that our xi is 1 plus 2i over n, so wherever we see xi, we're going to put 1 plus 2i over n. So f of xi is equal to 2 times 1 plus 2i over n plus 1 plus 2i over n squared. Okay, so that's how we get, and now we need to simplify that. So we've got, we times our 2n, we've got 2 plus 2 times 2i over n is 4i over n, plus, let's square that out, we get 1 plus 4i over n plus 4i squared over n squared. Okay, one more step to simplify. We've got 2 plus 1 is 3, so we've got 3 plus 4i over n plus 4i over n is 8i over n plus 4i squared over n squared. Right, so that was our step 3. Now we're going to multiply together in our step 4. Let me do that on the next page. Okay, so step 4. Multiply together. So we want to find f of xi multiplied by change in xi to get a formula for the area of our rectangles. We've just found f of xi to be 3 plus 8i over n plus 4i squared over n squared. And we want to times by change in xi, which we found to be 2 over n. Let's just times that out. 3 times 2 over n is 6 over n plus 8i over n times 2 over n is 16i over n squared plus 4i squared over n squared times 2 over n is 8i squared over n cubed. Cool, so we've timesed. Now we're going to look at our next step, step 5. Now in step 5, we want to add in our summation. So we want to sum all those rectangles from I is equal to 1 up until n of f of xi multiplied by change in xi. Right, so we do that. We're going to add in our summation. So we've got the sum from I is equal to 1 to n of this whole thing that we found in the previous step. So that's 6 over n plus 16i over n squared plus 8i squared over n cubed. Right, and just like in the previous example, when we've got a summation, we can split it over all of these different terms. So it's the sum from I is equal to 1 n of 6 over n plus the sum of 16i over n squared plus the sum of 8i squared over n cubed. Now again, remember that we can take out anything that doesn't have an I in it. So I'm going to take out the 6 over n, and then I'm left with summing up just 1, plus take out anything in the second summation that doesn't have an I in it. So I can take out the 16 over n squared, and I'm summing I, plus here again I can take out 8 over n cubed because it doesn't have an I, and I'm left with I squared. Right, now here I know what the sum of 1, the sum of I, and the sum of I squared is. If I go all the way back here, let's go all the way back up to the top. The sum of 1 is this, the sum of I is that, the sum of I squared is that whole story there. Okay, so let's substitute. Right, so this is 6 over n, the sum of 1 is just n, plus 16 over n squared multiplied by, here we've got n squared over 2 plus n over 2 plus 8 over n cubed. That whole story is n cubed over 3 plus n squared over 2 plus n over 6. Right, now we're going to times n and simplify. 6 over n times n is 6 plus 16 over n squared multiplied by n squared over 2 is 8 plus 16 over n squared multiplied by n over 2 is 8 over n plus 8 over n cubed times n cubed over 3 is 8 over 3 plus 8 over n cubed times n squared over 2 is 4 over n plus 8 over n cubed times n over 6 is, let's have a look, 4 over 3n squared. Okay, cool. Now, can we simplify that in any way? Let's look at our numbers. We've got 6 plus 8 plus 8 over 3. Our constants give us 50 over 3. Then we've got 8 over n plus 4 over n gives us 12 over n plus our 4 over 3n squared. Okay, and our last step, step 6, is to just add in our limit. Okay, step 6. We now want the limit as n tends towards infinity of our whole sum. F of xi. So it's the limit of that whole thing that we've just found there. So it's the limit as n tends towards infinity of this whole story. 50 over 3 plus 12 over n plus 4 over 3n squared. Again, 12 divided by a really big number tends towards 0. 4 divided by 3 times a really big number tends to 0, which means I'm just left with 50 over 3. Go back, check if you've answered your question. It says evaluate that integral. So it hasn't asked you for an area. You've just had to evaluate the integral. So the integral is 50 over 3. And you can check it by actually calculating the integral. Now you might think, sure, this is really long. There's lots of steps involved. And it's true, there are. As you get more used to working through Riemann sums, you can leave out more and more of the sub-steps. You might want to do it in one go. Have a look at how they approached in past papers. But if you just want to be sure and go step by step, it's okay to show all of these steps along the way. You only need to use a Riemann sum when asked to do so in a question. So if you're asked to integrate something and it doesn't stipulate Riemann sum or rules, go for your rules. But if you're asked to use a Riemann sum, this is the method that you will be using.